So a good way to highlight this selectivity is in an intramolecular reaction of an aldehyde with a neighboring ketone. So if you imagine the equilibrium where we treat this with sodium hydroxide, we're going to assume there's probably also a little bit of water around for proton transfers. We can actually make a number of different enolates in this process because we end up having a hydrogen here, a hydrogen here, and a hydrogen here. So since acid-base chemistry is very fast, we can really imagine any one of these being potential reactants to go towards a certain product. So if we look and try to number the product, this will give us some information about how this molecule had to cyclize. Oops, I skipped a number. We're going to call this one 3. This will be 4, 5, 6, and 7. And if we label these, we see that the methyl group next to the ketone is 1. So we can start numbering our groups accordingly on this starting molecule 2. So this is 1, 2, 3, 4, 5, 6, 7. So now we see that along the way, we ended up making a bond, ooh, pink, between 3 and 7. Which means this had to have come from this enolate reacting with the aldehyde. So if we go back to numbers, this was carbon number 3, this is carbon number 7, and this is the reaction that takes place that will lead to the product. So we're going to go through the different scenarios to explain why this one was favored and the other ones were not. So this would have been after proton transfer. You get this hydroxy ketone. Since we have the double bond, we know we're also going to have additional sodium hydroxide come in to deprotonate this alpha hydrogen and kick out the hydroxide group. So how about these other options? So I'm going to draw out the final enolate that we could have, and that'll be from making the aldehyde enolate. So when we have these types of cyclization products, you really want to be considering each one of them and how they might be able to react. So in looking at this first example, we can see that this would lead to a potential reaction between 1 and 7, because the enolate will be our nucleophile and the aldehyde would be the electrophile. In order to make this, though, this would lead to a very large or medium-sized 7-membered ring, where we'd end up with this ketone, and this would be the alcohol. And this would potentially, hypothetically, further eliminate to give a cycloheptene. So the reason this doesn't work is that 7-membered rings are actually slow to form. We can rationalize this, the reaction of making a 7-membered ring versus a 5-membered ring, and that a 5-membered ring is much closer. So there's a higher probability that these two groups will be able to find each other quickly and react. And we're going to assume that all of these different reactive intermediates, all these different enolates, are actually in equilibrium with each other along with this dicarbonyl compound. So the rate limiting step will be the attack of an enolate onto the carbonyl, not formation of any of these enolates. So formation of enolates is with sodium hydroxide is usually not very sensitive to sterics, so we could assume any of them could be made. So we're really looking for which cyclization will be the fastest. If we go and look at the last example, now we have a reaction taking place between carbons 6 and 2. If we were to hypothetically draw this arrow, this will also make a 5-membered ring. But now we're going to use a slightly different argument for why this process will not be as favored. So you can see that, once again, reactions of aldehydes on ketones are probably going to be quite a bit slower, and the equilibrium will be less favorable. So once you get to this intermediate, it can still go backwards and actually do the reverse process. So since this intermediate we made has this all fully substituted carbon, the steric of attacking and making this center is actually going to be slower as well. So the other thing to keep in mind, and this reinforces this, is that aldehydes react faster than ketones. So the attack on the aldehyde will be faster. There's only a hydrogen next door. And so this central process will be the one that actually is productive overall and would lead to the major product. And so we're using two different elements. One is what is the size of the ring, and would we expect that to be fast? Usually 5 and 6-membered rings form very, very quickly. 4-membered rings are too small and strained. And whenever you go to anything larger than 6, these also actually have more ring strain, and also they're just farther away, so it's less probable the two ends will find each other quickly. 5-membered rings are generally the fastest to form in a cyclization reaction. And will also generally outcompete other processes. The second big consideration here is what's going to be faster, attacking an aldehyde versus attacking a ketone, and attacking the aldehyde will also win out every time in this competition. So now we need to start doing some practice of, let's say we see a product from an aldol condensation. Can we predict what the starting materials were? So doing a bit of retrosynthesis when we see some of these groups. And so one of the keys that we're looking for is, again, identifying two elements. One is this alpha-beta unsaturated carbonyl compound. So we see we have a double bond here, here, and here. And we have the corresponding carbonyl adjacent. So this will tell us something about our reactive partners. The carbon that is next to the carbonyl, that used to be our nucleophile. So that's where the enolate came from. So along the way, it means that this bond overall was broken. And the first intermediate we would have is the hydroxy ketone. So this is prior to the actual aldol reaction. Because we know that in order to do this, we would need to deprotonate this intermediate to get to this enolate in order to have that final dehydration reaction take place. So now we can disconnect one more time, rationalizing that this was our nucleophilic enolate carbon. That means that the alcohol used to be our carbonyl. So now breaking this bond fully open, we're going to ring open the system. We can number the carbons too, if that helps us keep track. 1, 2, 3, 4, 5. And we can predict what the product will be. Or excuse me, the starting material would be. And this gets us back to this simple diketone. So we can check ourselves by going back to the numbering scheme. 1, 2, 3, 4, and 5. So we see where we had this nucleophilic carbon that used to be here at 1. And that means that our electrophilic ketone was 5. So in an intramolecular sense, we can have an aldol type reaction to condense onto a ketone. These are just a little bit slower than you would have in the case of aldehydes. And frequently, these will be accompanied by heat as well. And the heat will also let us know that we're going to fully dehydrate the molecule after the attack of the carbonyl compound to give the unsaturated product. Let's try this process with yet another one. So going back again, we're going to break this double bond. Now we can try to do this whole process at once. If we recognize where this carbonyl is, now we can say the beta carbon to the carbonyl, that used to be our carbonyl compound. And the carbon right next to the carbonyl was our nucleophile. So sometimes it still helps to go maybe one more step back and draw that hydroxy ketone intermediate until you get a bit more practice at these. And we can also now start to number our nucleophiles and electrophilic centers. So we'd have 1, 2, 3, 4, 5, and 6. We make this 6-membered ring. And now going back, we can draw the same system. And maybe it helps to also keep a bit of the same shape along the way too. Where now that we see that we have this methyl group, which is going to be our nucleophile. We have this aldehyde here, that is our electrophile. We can always double check by counting again. And indeed, this does give us the correct starting material. If we were to deprotonate this methyl, it'd be able to attack this aldehyde, giving us this hydroxy ketone intermediate that would then dehydrate to give this eno. All right, so one last example. We're just going to skip directly, maybe not draw the alpha hydroxy ketone this time. We recognize that we have our carbonyl. The carbon next to the carbonyl will be our nucleophile. And that means if that is the nucleophile, the beta carbon was the electrophile. The electrophile will be a carbonyl compound. And if we want, we can also number these too. So this would be 1, 2, 3, 4, 5. So when we draw this out, we can have our ketone. This is 1, 2, 3, 4, 5. Oh wait, that was a methyl. So we have a methyl at the end and a methyl here. So once again, we get back to a symmetrical starting material. Going back, we see that this was our carbonyl. This was our nucleophile. And we can number these 1, 2, 3, 4, and 5. So in these last two examples, we also see that we had other possibilities for cyclizations. We did not see a 5 to 2 attack. We didn't see that because that'd make a 4-membered ring. That would be quite slow and high energy. That would not be a favorable reaction. So the attack of 1 to 5 and 4 to the other carbonyl, these end up being the exact same reaction. The reactions we don't see is the methyl attacking this carbonyl, because this would be a 7-membered ring. and this would be slow. So again, these follow the same sort of possibilities and options we saw on the previous slide, but it's a little easier since we give you the product ahead of time. We're just trying to predict the starting material.